Hello, this video is the first section in Chapter 3, Section 3.1. Chapter 3 is pretty much mostly about finding shortcuts to finding derivatives. And so in 3.1, we're going to be doing some basic shortcuts, ones for polynomials, x to a power, and for exponentials, e to the x, or in general, any base to the x. We're also going to learn about the sum and difference rules and the constant multiplication rule. So the way we normally find derivatives is we use the difference quotient. We take the limit and we have some complicated fraction that we try to deal with, simplify, and out pops the derivative if we successfully find the limit. But you can do that lots and lots of times and look for patterns. So for example, let's just look at polynomials, x to a number, x to a constant power. So here's x squared. And if you do the difference quotient on x squared, do f of x plus h minus f of x over h with the limit as h going to 0, and you do all the math. I'm not going to do it for this particular video. You end up with the answer being the derivative is equal to 2x. You may remember me saying something about parabolas as a function will typically have linear functions as the derivative, and here's an example of that x squared has the derivative 2x. Well, we can also do the same procedure, do the difference quotient for x to the third. And once again, I won't be doing these demonstrations for this particular video, but if you do the difference quotient for x to the third, plug in all the things, simplify, factor, let h get infinitesimally close to 0, you find this derivative right here. The derivative of x cubed is 3x squared. And likewise, so we can differentiate any of these polynomial functions, x to a number, and we get these derivatives. And after a while, you might start to see a pattern, right? If you look at each of those top functions and the derivative, the respective derivatives underneath, you might see some repetitions of numbers and x's and powers and things like that. So if you haven't seen this before, you might want to consider, in general, if I had x to the n for just some number n, what's the pattern? What would the derivative actually look like? So the correct answer for this would be n times x with an exponent one smaller than it was before. And you can check this formula right here to see that it matches each of the previous examples. And this formula is not too hard to prove. It's proved by doing Pascal's triangle, if you remember that, and a little bit of algebra simplification. And this formula pops right out. There's a very good demonstration of this in your textbook, and I'm happy to show you if you like. Just send me an email or log into my Zoom hours, and I'll show you how this works if you're really curious about the proof. It's in the most practical purposes. We're just using the formula. We don't need to know the proof of the formula. Okay, so that's the derivative of a polynomial function. And likewise, we can find shortcuts for many functions, not all functions, but there's definitely a bunch of functions that we can find shortcuts for. So I have here a table with a bunch of the shortcuts from 3.1, all of the shortcuts from 3.1 that we're going to be using. And there's more shortcuts in 3.2, 3.3, 3.4, etc. These are the ones we're starting off with these set of exercises. So you just saw the x to an n, that's a polynomial. And it actually works when n is not a whole number. For example, I could do x to the 1/2. And if you remember our little rule, which I put off the side of the screen here, let me bring back here, move me over here a little bit. So the derivative of x to the n, the number that was representing the exponent comes down in front as a multiplication, and then you still have a power here where the exponent is one smaller. So if you think of that as the rule, as the algorithm, then here we have an exponent of 1/2. So that 1/2 is going to come down in front as a multiplication, and then we're going to multiply by the same kind of power, same base, x, but the exponent is going to be one smaller. So one smaller than 1/2 is called negative 1/2. So that's the example right there. Similarly, we have exponential. So exponentials are something like 2 to the x, or e to the x is a very common one, or 1.15 to the x. These are all exponentials. X is the exponent, and the number is the base. And notice that kind of flips from the first one, the polynomial function, where x is the base. The number is the exponent. Here we have the number is the base, and the x is the exponent. So that's called an exponential function. And once again, it has a shortcut, which is very nice. The shortcut of an exponential function, the derivative of an exponential function, it's actually the same exponential function, b to the x, times the natural log of b. And then as an example, here's the 2 to the x function, and its derivative would be the same 2 to the x times the natural log of 2. So another shortcut rule for you to remember, write down in your notes if you don't want to memorize it. E, as I mentioned, is a very, very common base for exponentials, probably the most common base for exponentials. So we have the rule for e to the x. It's actually really the same rule as b to the x because it's just an exponential. You may remember from your precalculus that the natural log of e is equal to 1. So the natural log of e comes out to be a whole number, in fact, 1. So this is officially the derivative of e to the x officially is e to the x times ln of e. But ln of e is just 1. And anything times 1 is itself. So e to the x times 1 is just e to the x. So the derivative of the x is going to be e to the x. You don't have to worry about the ln e since it's going to get absorbed into the e to the x anyway. Okay, so the last couple of rules that we're going to explore in 3.1, and you'll be asked about in the homework, is combining some of these together, like combining two different polynomials together, or polynomial with an exponential, or whatever you have. So the idea here is that the function we are trying to differentiate is actually two things added together, right? So the example I have here on the right is x to the negative 3, which is sort of a, x to a power, sort of a power function. And the second one is 4 to the x. That's an exponential. And I, in fact, adding them together. So if you're adding together, oops, let's see if I can get that off the screen. Maybe not. Okay, so if you're adding together a couple of functions, they could both be of the same kind. They could both be exponentials or both be polynomials or whatever. Then you end up actually just differentiating each one separately. And this works for addition or subtraction. So that's the rule right here, is if you can separate parts of a function by a plus sign or by a minus sign, then you can just differentiate those things separately. So back to my example here, the derivative of x to the negative 3, the negative 3 comes down in front as a multiplier, and the exponent is one smaller than negative 3 is called negative 4. So that's the derivative of the first part. And then the derivative of the second part, that's an exponential. So the derivative of 4 to the x is 4 to the x ln 4. So I'm just sort of using each of the previous rules for each part of this function that's separated by a plus sign. It also works for a minus sign. This does not work for multiplication or division, my friends. So don't try to do this rule for two parts that are multiplied or divided together or exponentiated or anything else. It only works for addition or subtraction. Now, this last one sort of looks like a multiplication. You can see there's a little multiplication symbol in there. And what I have listed over here for the function type is k times f. But the key difference here is that k is a constant. It is not a function. It does not move. It's like 7 or something like that. It's just a number times a function. And when you differentiate a number times a function, the number does not change in any way, but you differentiate the function like you would normally using one of these shortcut rules, or if you can't use a shortcut rule, you could differentiate it using the difference quotient and then multiply the answer by whatever the k is. So here's an example of this over here. I have x to the 10, which is one of our polynomial type functions that we have a shortcut rule. And then 7 is a number being multiplied by that. So the 7 doesn't do anything, it just stays there. And the derivative of the x to the 10 part, well, we take that 10, we bring it down in front as a multiplier, and then you have one smaller exponent of 9, and we'll smush all that together to be 70 x to the 9. So those are just the sort of the simple starter shortcut rules that we're going to experience in 3.1, and they're going to ask you a bunch of computational type problems. If you're used to doing a lot of formulas and like computation type problems, you will like section 3.1. It is lots and lots of these using the formulas, the shortcut rules to find derivatives. Okay, and the last thing I have for us today in this shorter video is make sure that you remember to use your algebra. Some of these problems will be very difficult if you don't remember your algebra. I have three examples right here. So this first example I'll do in red. If you're color sighted, I am boxing this here in red. You have to remember that a exponential in the denominator can be written as a negative exponent in the numerator. So if I had the function y equals 1 over x cubed, none of these rules apply for this fraction 1 over x cubed. However, if I know my algebra and I can write this as y equals x to the negative 3, then our first shortcut rule does apply. This is x to the n, and the derivative of x to the n is equal to, well, that's the one we just used a bunch of times, n x to the n minus 1. So you have to rewrite this using algebra. So it looks like x to the n, and then the derivative will be dy dx. The negative 3 comes as a multiplier, and then I get one smaller exponent in my little power function there. So that's the derivative of 1 over x cubed. Okay, so second problem here, circled in blue. If I have y equals cube root of x, none of these rules apply to cube roots or roots of any type, but we can write a cube root as a fractional exponent, 1/3. And then I can apply my power rule again. I define the derivative. I bring that exponent down in front as a coefficient, as a multiplier, and then I'll do one smaller exponent. So make sure you practice your fractions. 1/3 minus 1 is called negative 2/3. And that's literally just subtracting 1 off of the exponent. So there's a second example of where algebra is really helpful in us using the shortcut rules to find the derivative. All right, my last example here, I'll do a little cloudy in green. And so this is a fraction type problem, x squared minus x over x. So if I'm asked to find the derivative of this function, x cubed, if I said it correctly, like this, there's no formula that we have right now that can possibly have the derivative of a fraction of two things. These are two things being divided by each other. There are some other formulas that are more complicated that may be useful here, but for section 3.1, we really want to emphasize use your algebra. So this is like some of the difference quotient problems we did, where you can either factor or you can distribute to simplify this. For example, I will use factoring, factor an x out of the top, and then I will divide. X divided by x is 1. And actually, I don't need to write the parentheses anymore because multiplying by 1 doesn't really do anything. So these guys divide out. And this is a new version of y. And I can find the derivative of this thing. This is two functions being added or subtracted together. So I'm going to find the derivative of the first part. The derivative of x squared is 2x. The 2 comes in front. I get one smaller exponent. What is the derivative of 1? Now, wait a second. Do we have a formula for the derivative of a constant? We have a constant times a function. We have different types of functions. How do we find the derivative of 1? Well, if you've had some calculus before, you may remember what the answer is. But let me also remind you that 1, if you like, can be written as 1 times x to the 0. X to the 0 is, in fact, equal to 1. So imagine this as negative 1 x to the 0. You bring the 0 down in front. The negative 1 does not change anything. You bring the 0 down in front. And then we have x to 1 smaller. But 0 times anything, 0 times 1, 0 times x to the negative 1, that is all 0. So our derivative, once we get rid of the 0 part, combine it together, is just 2x. Now this function does not exist for x equaling 0, so our derivative is only valid for when x is not equal to 0, because you can't have a division by 0 thing there. So, but the derivative function is 2x as long as x is not equal to 0. So that's an example of how to find the derivative of this fraction type thing by first simplifying algebraically. Okay, I'm going to do some more examples of, these sum and difference rules and exponentials and, constant multiplying and all kinds of things like that in the next video, where we're going to add in a few more of the shortcut rules. So I'll sort of do them all combined together. That's going to be it for today's video. In today's video, I tried to show you that there were shortcut rules for certain functions, and I went through 5 shortcut rules, explained them, and did some examples for those. So please reach out if you have any questions, and I hope you have a nice evening or a nice day or whatever time it is for you when you're watching this video. Okay, great.